where did my career in tsunami start? Well, it started in 2004 when, with EPIC, I visited areas affected by the Indian Ocean Tsunami. And for those of you who are old like me, who remember 20 years ago the news and about the tsunami, this was an incredible event. It was triggered by a large subduction earthquake offshore of Indonesia of magnitude 9.3, which ruptured, caused by a fault rupture of around 1,250 kilometers in length. So an enormous earthquake event, which triggered with a massive tsunami. And the tsunami inundated around 12 countries, creating a death toll of over 220,000 people. And this event actually triggered not just my career within tsunami and engineering, but also those of many others. So really, it was the first time, I think, that many of us in the community were aware of the devastating effects of tsunami. And tsunamis are always talked about, and earthquakes and tsunami are talked about rare events, but I list on this slide the number of events that have happened in the last 20 years, and there are actually 18 damaging earthquake and tsunami sequences that have happened all over the globe. Many of these you may remember, the Tohoku Earthquake and Tsunami of 2011, for example, that is actually the most expensive natural disaster that has ever happened. Kaikoura Earthquake and Tsunami is a smaller event, but again affecting New Zealand. The most recent Noto Earthquake and Tsunami also affecting Japan in 2010. The Maule Earthquake and Tsunami affecting Chile. Now, the losses associated with these events are quite high, not as high as the Indian Ocean Tsunami, but they're around $404 billion US. But what is remarkable is that many of these locations, unlike in the 2004 event, had very stringent seismic codes. So, for example, in Chile. And the buildings that were seismically designed were also devastated or largely damaged by the tsunami. So why is this? Because at the time when I started working in the field, it was thought that if a building is resistant to earthquakes, which are a large horizontal force, then they should also be resilient to tsunamis, and that's not the case. So the structure of the talk today, we're going to go through really some of the basics of tsunami engineering, because not a lot of people know this. So what are the tsunami actions on buildings? What is their size, their distribution? How do we analyze buildings for tsunami loads? And then exploring the relationship between earthquake damage and tsunami response. And finally, some of the implications towards both earthquake and tsunami design. So what are the actions from tsunami on building? We can roughly split these into 4 categories. The first category is horizontal loading. The horizontal loads are imparted when the tsunami flows pass by a structure, and these are hydrostatic pressures, hydrodynamic or drag pressures, and sometimes impulsive forces. We also get uplift forces in water, clearly due to buoyancy, and this buoyancy can be due to there being air pockets effectively within the structure. And when these form, then the structure is subjected to these upwards forces or uplift forces. In the field, post-tsunami, we often see that the corners of buildings are no longer supported by soil, and that's because that soil is scoured, is entrained away by the flow, and particularly around corners where you have very high velocity flows passing the structure. And finally, within a tsunami, there can be debris carried, which again can cause damage, either the damming of spaces, or you have large objects such as vehicles or boats hitting the structure directly. I'm not going to be talking about scour and debris impact moving forward, but I will be touching upon the other types of forces, the horizontal loading and the uplift loading coming from tsunami. But what I found returning from the field in 2004 was that very few facilities worldwide existed for the simulation of tsunami in the lab. And those that existed didn't necessarily represent tsunami in a realistic way. So I partnered with HR Wallingford, and with them we have developed some new tsunami testing facilities and a new way of generating tsunami. And over the last 20 years, effectively, we have developed 3 testing flumes within the HR Wallingford complex where we can simulate tsunamis. So they're just shown here. So what are we aiming to do when we're trying to simulate a tsunami in a lab? Well, we want to reproduce some of the physical characteristics of a tsunami. And in my case, I'm interested in the inundation part of the flow. But we need to still think about what does a tsunami realistically look like. This image shows a record taken by an echo sounder who was measuring the depth of the seabed at the time when the Indian Ocean tsunami passed below it. So it actually recorded the Indian Ocean tsunami trace. And what we can see is that you have a large wave. In this case, it's led by a trough, a negative component of the wave, but a tsunami can also be led by a crest. And in this case, the trough is followed by a crest. And if we look at the wave period in real life, it's around 23 minutes. So we're talking about a very, very, very long wave, which offshore may only have a very short wave height. But of course, as it enters the shoreline and the coastal region, that wave height can increase through shoaling. But this length, this wave period, is something that other facilities were not able to generate at the time when we started doing our physical tests. And with Wallingford, what we did was we designed a new type of tsunami simulator. And all it is a glorified tank. So it's a big tank that sits at the end of a flume, and it has an air pump, a pump that pumps air out of the tank, and a control valve which allows the air to flow back into the tank. So if you close the control valve and you're pumping the air, then you are lifting the water within the tank. And as the water rises within the tank, you're creating essentially a trough outside of the tank. And then as you allow air to ingress back, so you open the valve, you allow air to ingress back into the tank, the water level lowers. And in that case, you are creating a crest. And these waves that are generated flow along a flume and inundate the land. So it's a very simple system. It's basically lowering and raising the water level within the tank to essentially create and start these waves running along the flume. The flume that we're doing tests in, or the largest one that we've adopted so far, is 70 meters long and 4 meters wide. So this is a diagram because I couldn't take a picture of the entire flume itself. And on one end, you have the tsunami simulator, this tank. And on the other side, you have the test bed, essentially where we are measuring and looking at the interaction between the inundation of the tsunami flow and the structures or the defenses or other aspects. And what we are able to do is generate through the system very, very long waves. So these are some images of crest-led waves. So we've only got a positive crest for the tsunami. And we can reach periods of 160 seconds in the flume model environment, which corresponds to a real tsunami of around 18.8 minutes in real life. And we're working at a scale of about 1 to 50. We are also able to generate these trough-led waves. And again, here we're actually reaching wave periods of around 240 seconds, or approximately a 28-minute tsunami, which was, if you recall, the length of the Mercator wave, which I showed you before. We're able to accurately control the wave because, we have a control system that dictates how high and low we raise the water, etc. So we've also tried to recreate real tsunami traces. So the top image shows the Mercator recorded that I showed you before, and how we simulated it. The red is our simulated in the flume record, and the bottom image shows you also the Tohoku tsunami trace that was measured, and our ability to simulate that. Note that there's quite a jump there in crest, etc. So we have a good control over simulating tsunamis. So tick, we solved the problem of simulating tsunamis. What have we done with that? Well, over the years, we have essentially investigated several aspects of tsunami interaction with the coast. We've looked at run-up, which is a measure of seeing how far the tsunami goes inland. We've looked at how coastal walls can be used to react against tsunamis or defend. We've looked at natural defenses more recently, a scour around buildings, and I'd like to focus today on really some of the tests that we've been looking at on buildings themselves, because that's what has helped us understand how tsunami flows interact with the built environment. I'm going to show, and hopefully this will work, and it won't be a total disaster. There we go. A video of, these are some of the tests that we conducted in 2018. This is a row of buildings protected by a seawall, and the seawall breaks. The flow coming in is a tsunami of around 50 seconds in the flume. So it's not one of our longest tsunami, but you can see that the water keeps coming and coming and coming and coming and coming. And it just shows you a little bit the ability of the facility to really simulate those long period waves. You can also see there's a lot of cabling, and that is because we are monitoring the structures in different ways. We're looking at pressures, we're looking at loads, and that has given us a number of profiles of what the loading on structures looks like from tsunami. And what we found was that actually what was assumed in the codes of practice is not actually what we recorded. So in the codes of practice, the assumption is that the tsunami wave arrives at the structure, it hits the structure, causing a large impulsive load, okay? And then as the flow sort of stabilizes around the structure, you have a quasi-steady sort of component or pressure that is acting, that slowly goes away as the flow passes the structure. In our tests, we don't see the impact at all. We don't see that massive spike at the beginning, but rather we see a bit more of a gentle rise and lowering of the forces. And this is because the assumption made with this big impact force is an assumption that comes from looking at flows interacting with walls that are full width. Okay, so they fully stop the flow. So you get this initial impact because the flow is stopped fully. However, structures, buildings don't stop the flow completely. The flow tends to flow around, and particularly as the tsunami is a slow rising flow, I mean, it's fast, but it's almost quasi-steady, then you don't see that impact, but rather the water passes by the structure or is able to go past it. And we've used some mathematics to basically show that actually the tsunami flow around a building are quasi-steady. And we've developed, to go with that, some very simplistic relationships for predicting what the forces from tsunami flows are on a structure, where we take into account the blockage ratio of the buildings, which is essentially the urban density. So how much does a building block the flow? And we also take into account a drag coefficient, which is a typical thing you would have within any flow around an object type of analysis, and the Froude number. And with these three parameters, we can basically estimate for any height and velocity what the forces are going to be on the structure. So we've tried to develop an engineering type of tool, a simple calculation that can be used for estimating the forces. So great. we now have some forces. Okay, so how do we apply them to a building? And how will a building respond to these loads? Okay, so that's another area that we have been working on a lot. And I just want to start to show you this figure. Because what was expected at the time when I started working on tsunami engineering was, again, this idea that a tsunami loading was similar to the loading from an earthquake. Now, the loading from an earthquake is fast, it's cyclic, there are lots of cycles, and essentially the cycles are of large strength only over a very, very short amount of time, right? So each cycle is high frequency, so has a very low time of impact, essentially. Tsunami is totally different. A tsunami is a quasi-steady, long duration flow. And so the concept of ductility that's used within earthquake engineering to resist earthquake loads cannot be used within a tsunami. So essentially what happens is the tsunami arrives at the structure and it pushes the structure and it continues to push the structure and it pushes and pushes. And when the structure yields, it continues to push. So the structure yields and it basically then collapses. And what we found mathematically is that once the structure is yielded under a tsunami, effectively, because the flow continues to push it, you get collapse straight away. And you cannot rely on the non-linear capacity, so that deformation capacity that we do in earthquake engineering, because once it's yielded, it's gone. And so what we did was we developed a analysis method that sort of took this into account, but took into account also the nature of the tsunami loading. So in earthquake engineering, we use something called a pushover analysis, where the loads are applied in an inverted triangle to the side of the structure, as shown on the left-hand side of this figure. And this type of loading essentially creates large moments at the bottom of the building. You have a large lever arm and you have a large moment at the bottom of the building. And we use this a lot in earthquake engineering as a proxy for the dynamic shaking of an earthquake. But we know that it's not very good as an analysis method for structures because it really doesn't take into account the cyclic loading component, etc. In tsunami, what we did is we reversed the concept. So we started at the base and we said, okay, the flow starts at the bottom and rises. But essentially, if we think of it as a hydrostatic type of loading or similar, then we have a very similar sort of triangular distribution that we apply, but it starts at the bottom and rises up. The nature of these forces is that actually it induces a large shear at the base of the building and not the large moment that the earthquake does. And this is a key concept. So the response that we get under tsunami loading and earthquake loading is very different. So we wanted to develop this approach a little bit further so that we could develop what we're calling a variable depth pushover in a way that we can analyze the structures properly. And we developed two approaches. One saying, okay, you have a constant depth and you increase the velocity of the flow, and that's what we're calling constant depth pushover, or we have a variable depth pushover where you have the same Froude number of flow and you're increasing the height. So we're applying the loads. The loads can be applied in different ways. And we've found essentially that the variable depth pushover is a much more reliable approach to analyzing the structure. So the bottom descriptor here. We had to look at how do we apply the loading to the structure, because it's not simple. As you're raising the loads, you are activating new nodes. So you are applying forces to new nodes that were not originally, didn't have any force applied to them earlier in the structure. So we discretize the load such that at each node you have a time history of forces. And the nodes that are higher up in the structure have zero force to start with, and then they start to attract forces. This allows us, by having a time histories of loading and discretizing the loads in this way, it means we can actually start to activate different nodes as they get inundated, both for horizontal loading, but also for vertical loading. So we can take into account the effects of buoyancy. Moreover, what we can do is take into account the fact that during the flow, the structural conditions change. How do they change? Well, if we take a reinforced concrete frame building, like the one shown here, initially when the flow is low, you will have intact cladding or intact infill. But as the tsunami loading increases, as the water depth increases, some of those infills will give way. They will collapse out of plane. And therefore, what happens when they do that is actually the area over which the pressure of the tsunami is acting reduces. So the forces reduce. And we can take that into account. So we can take into account that reduction of force due to the collapse of the infills, but also the redistribution of forces across the structure. So, internal columns, if you see in A here, the internal columns have no fluid loading, but once the structure becomes permeable, i.e. the external walls collapse, then the internal columns start to pick up loading, etc. If you look at the case of B, what we find is if the infill is still intact on the second story of the structure, while the bottom is inundated, you have now a big air void and very large vertical forces that are acting because you've got an air void engulfed in water, essentially. And until those top story infills collapse, then you're not releasing that vertical load. So we can take into account effectively the change of loading in the structure. So this is just another diagram to show how, particularly in the case C here, you have an enclosed air void, which causes very large buoyancy forces on the slab of the first story. And when you've got the collapse of the infill on the first story, then that buoyancy load basically disappears, and you get water flowing above as well. This is just an animation of a simulation that shows you how a structure, and this is an infilled structure, a reinforced concrete structure, responds to a tsunami. And if I can set it going, what you can see is the water level is increasing. As that water level is increasing, the base shear on the structure increases. But you also have a point at which you have a drop. So if you see halfway up the curve, you get a drop and then a pickup again of force. That drop is the lowering, that's the collapse of the infill, essentially, that is releasing loads and reducing loads on the structure. So it then continues to carry loading up to a certain level and then fails. You get this sort of abrupt drop in strength, and the structure continues to essentially lean over until it's failed completely. What can we take from here? And sorry, I might have lost you on the way. I hope not, but let's summarize a little bit. Firstly, that non-structural elements are really important. So the infill walls, because of their large area, they attract a large loading from the tsunami flows. And so ignoring them is unconservative. So we have to take into account the fact that there are walls that may attract loading, and because they attract loading, then pass that to the main structural elements. Because if we don't do that, then we're underestimating the loads. But it's also too conservative to not consider the fact that they may fail during the flow. And if they fail, they're releasing the loading and reducing the loading on the structure. We can use nonlinear static methods to analyze tsunami performance, and we can do that very well. And we can use something we call the variable depth pushover very well to do that. And this is an approach that we've developed and is now fully available. And another observation is the fact that if we use nonlinear static, this pushover approach for earthquake and tsunami, we get a very different response of the building. So I mentioned initially having an earthquake pushover imparts a large moment at the base of the structure, okay? And that results in a lower base shear capacity of the structure, lower capacity to take horizontal loads, but the structure can deform quite a lot. In the case of tsunami, because the loads start at the base, they are eliciting a different response in the structure, much stiffer response, okay, and a much stronger response. So the structure is actually stronger under tsunami loads than it is under earthquake loads, but it is also not ductile. It can't take those large deformations. Why is that? They're both horizontal forces. Well, effectively, they're quite different. They're fundamentally different forces in how they apply to the structure. So if we take into account this example with New Zealand football players, basically, a tsunami is on the left. It attacks the legs of the building. It attacks the legs of the structure. Okay, it attacks it right from the bottom, and it tends to basically unseat those legs. You know, it swipes the legs off their base. The earthquake instead attacks the top of the building. It tends to try and rotate the person, so it'll try and topple them over. Okay, so if we take that example, you can see that they're fundamentally different. And the way that you are resisting those forces as a person is different. So the structure also is doing that. So we're looking at two quite different forces, both horizontal loads, but acting in a different way on the structure, on those bodies. So in tsunami engineering, we've been really blessed by new codes of practice that have come into play for looking at tsunami actions and how to design for tsunamis. And one of the most well-known or most well-used is the ASCE 7 standard, which Chapter 6 contains the tsunami assessment or analysis code. And you don't have to know a lot about this, but what I wanted to show you is that how thinking has evolved. The ASCE 716 started with the first check that it conducts is to say, well, take your earthquake resistance, your pushover analysis from your earthquake analysis of a structure. And it's this curve that you see at the bottom here, similar to the ones I've shown you before. Take its maximum strength, okay, reduce that to 0.75, add a safety factor on top of that. So we can basically assess, we say, well, if we take that pushover, then we have a sort of a maximum strength that the structure could potentially achieve with all overstrength considered. And basically, if the tsunami loading is less than this value, this 0.75 times 3 times the base shear at design, then you don't have to conduct any further analysis. You're okay for tsunami. Okay, so that's the check. So the check in the Code of Practice in 2016 was take the earthquake response and do a few calculations and then compare that to the tsunami loading that would be applied. But as we've mentioned before, the earthquake response is not the tsunami response of a structure. So in this diagram, I show you the earthquake response of this particular building. We're looking at a building which was actually a 5-story structure built to Japanese code, seismic code. And the structure here has an earthquake response shown by the gray curve at the bottom. Okay, that's its design response. If we apply the factors, you get to this gray line here, 0.75 omega EH over 2. Okay, the applied tsunami loading on the structure is higher. It's this black dashed line. Okay, so according to this check in the Code of Practice, the structure would fail. Okay, so you would have to redesign the structure, and what they've told you to do is to basically enhance the seismic design, make it even, seismically stronger. But But actually, if we look at a real structural response under a tsunami analysis, we see that actually the tsunami capacity is much higher than the applied tsunami forces. So if we conduct this nonlinear static analysis, the variable depth pushover, we actually see that the structure can resist the tsunami loading. So it would pass, essentially, this first check. The ASC code then goes on to say, well, you know, the loading on individual elements can be higher than just a normal distribution. You know, we can have enhanced drag on individual elements. So you need to check the structural components as well, not just the system as a whole, not just the structure as a whole, but also the individual components. And if we look at our structure that we're analyzing here under the tsunami pushover curve, it would fail these checks. We are having some elements here, 1011, 301123, etc., that are failing in shear, and they're failing before we reach the dashed line of the tsunami force, which is at sort of this 1.5 value. So yes, the structure would actually fail when we're looking at the component checks. But what this VDPO analysis gives you is it tells you which elements are failing. And so it provides you a way of redesigning just those elements rather than designing the entire structure from scratch. So we find that by using this tsunami pushover analysis, you can actually come up with a less expensive design and a more appropriate design of the structure. So you can design your structure and take into account exactly where the failures would be from a tsunami loading. And we have developed a version of the VDPO that is compatible now with the ASCE 722 version and is referenced in that code and available on commercial software. And we're making it also available for researchers. So again, we need to really embrace the fact that tsunami analysis and tsunami responsive buildings is different from earthquake responsive buildings. And one of the things that we found consistently in some of the case studies that we've been running is the fact that even seismically designed buildings fail in shear. Now, shear is something that in seismic design, we design out. So we assume it never happens. But actually here we're getting a precipitated failure through the shear failure of columns at the base of the structure. So if we look at collapse through global deformation shown by this vulnerability, this fragility function for, again, this was a 10-story reinforced concrete building. If we just look at, if we ignore shear failure, we get a peak force, tsunami force of about 1.2 kilonewtons times 10 to the power of 4. Whereas actually, if we consider the collapse triggered by shear failure of the columns, we see that that's reduced to about 0.5. So the shear failure of columns in the ground story is a big issue. And this, in theory, shouldn't happen in seismic design, okay? But it does happen because the loading is different. So really continue to think about that difference in loading conditions. And let's extend this one step further. What happens if you have an earthquake and then a tsunami? Okay, so far we've sort of looked at earthquakes separately from tsunami, but these things happen in sequence in many locations like Indonesia. So what happens if you have first the earthquake ground shaking and then you have the tsunami? We ran a number of different analyses, for example, on structures, seismically designed structures, where we ran first some earthquake ground motions, okay, allow the structure to come to a rest, and then we ran a tsunami pushover analysis. And the idea was to see, you know, to test these structures under different levels of damage caused by the earthquake and then see how they would respond under a tsunami. So, you know, if the earthquake took it to damage state 1, you know, what would be the tsunami capacity and so on. Damage state 2, damage state 3. And this is what we found. And we found that actually the fragility functions that come out of this analysis are pretty much the same. So what this fragility function shows us on the left-hand side is what is the tsunami capacity, essentially? What is the tsunami fragility of the structure under different pre-existing damage conditions. So with the green shows the band of response we get if we have damage state 1. This lighter orange, basically damage state 2, darker orange, damage state 3, and no earthquake, you have the gray area. And you can see that actually the change in fragility is very small. All of the curves are very, very close together, basically implying that the earthquake damage has absolutely no effect on the tsunami response of the building. Okay, and that seems contrary to what you would think. Okay, and I'll explain this a little bit further. But from our analysis, it looks like pre-earthquake damage essentially has no effect on the collapse probability under tsunami loading. And if we look at local performance, so if we look on the right-hand side, so we don't look at just the global response of the structure, but actually failure precipitated by the shear collapse of the columns, we see even less effect. Basically, we're getting the fragility functions to be almost coincident, and of course at a much lower tsunami force, because the shear failure is causing that collapse to happen early. Here is where I found a lot of resistance from my colleagues who go out in the field and, like myself, look at damage after tsunami. And it's important to consider that in places, for example, like the Tohoku earthquake and tsunami, the damage that is reported is a combination of earthquake and tsunami damage at the end. There is no separate analysis in the inundation area of the earthquake damage before the tsunami happened. It's a combination of the two things. If we look at some of that data from Tohoku, which is the most detailed data that's out there at the moment from post-earthquake tsunami event, and we look at the distribution of damage, what we have here is a histogram of the number of buildings damaged and the different states of damage that they're in. So damage state 1 is low level of damage, damage state 4 is effectively collapse. What we find, if you look very carefully, is that the damage from the that is between damage states 0 and 3 is recorded in buildings that have been affected by earthquakes, the earthquake ground shaking quite significantly, but where the tsunami inundation was very low. And if instead we look at the collapse 1, 4, we see that predominantly it's in areas that were affected by very large tsunami inundation. And it doesn't matter what the earthquake forces were, but it's very large tsunami inundation. So if you actually look in detail at these, you can see that this is the case, because remember what I said before, when your structure yields under the tsunami loading, it will collapse. That basically is saying that until the structure yields, the tsunami hasn't got an effect. The structure will go back to its original position, will be elastic, and will have no damage from the tsunami. It will have non-structural damage, but nothing to the structure. So the tsunami is actually quite a binary, it causes quite a binary response. The structure is either standing and is okay, or it's collapsed. So, and the threshold between the two is the yield of the structure. And so what we get is actually that all of the damage states that are lower than collapse are generated effectively by the earthquake ground shaking. And it doesn't matter what the tsunami force was, so long as it was low. Whereas the tsunami will collapse the structure or it will be fine. And we see that reflected also in different locations. And you can see that where you have a low tsunami height, so the 2 meters at the bottom, you see a distribution in the damage. So you can see that the earthquake, which shook the ground, was quite large and caused, a distribution of damage. And then, of course, you've got the peak also from the tsunami. But in areas where you have high tsunami damage, you have and low earthquake shaking, you actually have the tsunami that is dominating the response. It's causing the collapse. So it's not a perfect analysis of the data, but it does actually, when you start looking at it from this perspective, show that the tsunami and the earthquake are affecting the buildings differently. So key observations is that the quasi-steady nature of the tsunami loading means that the collapse occurrence is determined by the strength of the building under the tsunami loading, which is a different strength than under the earthquake loading. It's a higher strength. Once the building yields under the tsunami, it will collapse because of the duration of the loading, because the tsunami keeps flowing and flowing. But if it doesn't yield, then the damage from the earthquake is the one that actually dominates the overall damage state. So it's almost like you can analyze the structure under earthquake and tsunami separately and take the worst case of the two. So what does that mean for earthquake and tsunami design of buildings? Well, if we're looking at both of these things together, we need to consider the fact that now you've got two forces acting, both horizontal, but actually different. So again, you've got this poor American football player who's in the middle there, who's being attacked both from the top, which is the earthquake, and from the bottom, which is the tsunami, and he has very little hope, poor thing, of standing up. But still, we need to give him the strength or the reinforcement to be able to compete with these two different forces. So how do we do that? Luckily, there's a way. And the way comes specifically because the response of the building to tsunamis and earthquake is different. So you need strength in the structure to resist the tsunami. And you need ductility, so that flexibility in the structure to resist the earthquake loading. But you can achieve with the same design a very high tsunami strength and a very ductile earthquake response because of the forces and how they act are different. So what would I do to design a structure for both earthquakes and tsunami? Well, this would be my proposed method. I would go through the classic earthquake design to start with. I take my structure, design it for my seismic loading with the full capacity design. And then I would use the ASC 722 code, okay, and take the first initial seismic design of my structure, subject it to my tsunami loading, both vertical and horizontal, using a nonlinear static analysis, and check the response in that case. Most likely, the overall response of the system will be fine, but there may be issues with particular elements, things like the columns of the ground story. So I would strengthen those to meet the tsunami design requirement. And you just check bending and shear capacity of all the elements to make sure that that's fine. And hopefully that would give us an economic design. On top of that, I would start to think about other aspects that I could take into account in my design choice to start with, such that I can actually reduce loading from both cases. So one of the things I can do is, for example, separate infill panels from the surrounding frames and have weaker infills. One, so that they can be blown out by the tsunami, but that's also useful in having a good response from your under earthquake situations. If I needed lateral restraint, if I needed a stiffer structure, I might choose bracing over walls because bracing allows water through. So considering that, the bracing will be good under earthquake conditions, but will allow water to go through under tsunami loading. I would potentially use shallower beams so that they don't trap the air underneath them. And this can work within the context of capacity design for earthquakes, where we're designing our beams to be weaker than our columns. I might even design blowout slabs, so to allow the slabs to lift up in the case of a tsunami loading that has high buoyancy loads. I'd make sure that there's redundancy in some of the vertical load carrying elements, so that if there was debris impact from something floating in the tsunami flow, then I would avoid progressive collapse. And most likely look at also implementing deeper foundations and ring beam foundations to resist scour effects. So this is some of my ideas of what I would do to look at both earthquake and tsunami design. And you'll be happy to hear that that's coming to the end of my talk. I still think there's a lot to do. There are significant limitations with the work that I've presented. We're looking only at certain case studies. We're ignoring some types of some other parts of the tsunami loading, like scour and debris. But globally, we also need to be able to predict how big our tsunamis are going to be. And there is a lack worldwide of tsunami hazard maps. And that is something that I think is a gap that we should be trying to fill as a community. We need to not only conduct research, but actually influence policy and get some of this stuff into practice, into codes of practice, etc. And we need to be able to work with other disciplines to move this forward. I would not have been able to do this work without collaboration with a whole number of different people, including, coastal engineers, fluid mechanicians, earth scientists, social scientists, etc. So I do really believe in this multidisciplinary approach. So I leave you here with a thank you, and I provide you both my details at UCL and also the details of my email at TU Delft, where I'll be starting as head of Department of Hydraulic Engineering in June.